Questions? All right. Shut that one down. No changes. Okay. So last time I was doing a data dump on you about networking. And I was mentioning the RFC, which I believe I now have posted several of the RFCs up in the supplemental reading section on BBLearn. This is the request for comment document that describes the actual protocol and how it works. I wanted to go into this a little, and then I'm going to step back and explain some other things about this. But this is what the data going across the network looks like. Okay, top to bottom, left to right is the order in which things come across the network, and they're read and handled. So if you read this into a data structure, the very first byte will be way up here, the last byte will be down here. Now, what are these bytes? I think I have those on the next slides. No, wow, what happened to my other slides? Okay, version tells us which version of the internet protocol we're using. Version 4, version 6. IHL, the next section, is the internet header length. Internet header length says how many octets, bytes, 8-bit things, are in this header. Now, we need that because the very last part of the header down here is options. And if you have options, you can have many options. And so the header length allows us to expand those options. We also have padding because we want to make everything in terms of a 32-bit word. Actually, so I lied to you. Internet header length is the number of 32-bit lines in the header. Because typical header length is 5. 1, 2, 3, 4, 5 header with no options. So if it's 5, you have no options. 6, you have one option line, etc. And so the padding always brings it to a multiple of 32 bits in width. Type of service we'll have is a quality of services and push something that's urgent that you have to push through, things like that. Total length is now, that's number of octets, in the whole message. So your data appears after this that you're sending across. This is just the header. And the total length includes the header plus the data. Identification is used when I create a data packet and I want to ship it across the internet. I give it a number. This packet could be, say, 4,096 total bytes. An intermediate system may say, hey, I don't send anything bigger than 1K, 1,024 bytes. So it'll break mine up into 4 chunks, actually 5 probably, because it'll put a header on every one of those chunks. This identification specifies which and what was the number of that original packet. The fragment offset here then tells me how many bytes into that original packet does this one actually start. So the first one will start with 0. The next one would be, okay, I cut off 1,024 bytes for the first one when I subdivide it. So the next one I'll have the offset will be 1,025. Okay. Flags, there's certain flags we use that we use to coordinate things. Is this an urgent method? Some of those, I'm not going to go into details there. Time to live. I love this name. As I was drawing earlier, in the internet, I go from my machine to another host, gateway, which goes to another one, which goes to another one. Each of those transmissions from one machine physically to the next machine is called a hop. Now, because the internet can make decisions and say, oh, hey, I want this route, it is possible you get a circular route. each time you do a hop, you decrement the time to live counter. When it gets to 0, it says, we're done. This one failed, and it throws it away. Now that's cool because there's actually a tool out there called traceroute, which it says, hey, I want to know what are the addresses of all the intermediate machines. So I'm going to send a data packet out from here to that destination with a time to live of 1. Goes out to the first hop and says, oh, it's 0. You're done. And the internet has some built-in error control. So it sends back a message saying, I threw away this packet. It wasn't far enough. Now, so it gets the address of the first person threw away the packet. Then it sends it again with time to live 2. And the next host then sends back the packet. Then time to live 3, then time to live 4, then 5, then 6, and it builds up the list of all the intermediate hosts until you see it. How many do you think it would take to get from here to a Google server? Closer to 20.
Oh, really?
Now, when I first got here, there was the limit, absolute limit was 32. And they never, and you could get anywhere in the world in under 32 hops. Not the case anymore. There are just so many intermediate ones. I don't think I should have actually tested if I had it.
So there's now more than 32 places.
There's just so many intermediates is the problem. Let's see. I don't think that's installed on this one. Yeah. I'll have to get an example of that. Okay, I lost my screen share. But it's a kind of cool thing, and it's used by a lot of people for security analysis and things like that. Where is it coming from? Where is it going? Okay, let's try that again. There's my slides. Protocol. The protocol field says, okay, this is the IP is a host-to-host protocol, machine to machine. The higher level, we're trying to get application. I will talk later about, we have a couple different transport protocols. We have TCP, the transport control protocol. We have UDP, the user data. User datagram protocol. Thank you, UDP. We have ICMP, the Internet Control Message Protocol. That's where it comes back and says things like, I dropped that packet for you. Each of those is a different service or protocol implemented in your machine. Each of them has a unique number. This number specifies to the receiving machine, who do I give this to? Do I give it to the TCP protocol engine? Do I give it to the UDP protocol engine? Do I give it to the ICP? They're all different programs, different services. Okay, I'm lying to you. Most people merge those things together, but there's several others that aren't merged together. But the idea is they're independent. So this specifies where it goes. Header checksum. The header checksum, we want to make sure there's no errors. So we do a checksum. It's basically a mathematical calculation on the header. It's like a hash, but not as complex, and it gives you the value. So what they do is they do the header checksum on the full header, assuming the header checksum field itself is all zeros. Because and then when somebody receives it, they say, well, let's do a checksum on the header, assuming the header checksum is all zeros again, and then do the calculation compare. Because you can't do a checksum on the value while you're checksumming it. The value you're calculating. So there. Source address, that's my 32-bit. Who's sending this? 129.101.100.1. That's who's sending it. Who's receiving it? 192.168.1.5. Those are those addresses. And then options. And there's lots of different options that we can do in there. I'm not going to worry about it. So in reality, if I look at this, there's a tool called TCP dump. TCP dump allows me to look at messages going across the network. For analysis purposes, I can copy everything that goes out of the network and store it in a packet capture file. So this would be an example of some packet capture file. There are tools out there like Wireshark that we'll talk about later that allows you to just do this and create these packet capture. TCP dump itself will create them, etc. The N basically says, don't try and go out and figure the name of this machine. You know, I've got a 129.76.210.185. Don't go out and try and figure out who that is. That just takes too much time. X is show things in hexadecimal. And then -R is recover it from this packet capture. So I'm not reading it actually from the internet, but that's just, anyway, what I do is I do this TCP dump. It gives me all this information. Okay. Part of this is the time the packet was received. It was an internet protocol packet. Here's the source host and port. I'll talk about that later. It was sent to the destination host and port. Here's something about the flags. It had an ACK and a WIN. We don't worry about all those. Here's the raw bytes we see. That's important. So we get these raw bytes across the internet. These are the line numbers. So here's the first line of bytes. This first one is the version number, version 4. Next one is the internet header length, 532-bit words. This is the quality of service and op things. It's all zeros, so it means there's nothing special about this one. These 4 bytes are the total length. Now, how do I read this? This is more than one number, right? We read it like we read normal decimal notation. This is hex. So this is 4 plus 3 times 16 plus 0 this time times what is 16 squared, so 256, etc. So this is the total length of the message. Notice I just said we're reading things that way. The order the bytes came across the network and how I read them, I have to interpret these. This byte comes first, then this one comes across the network, then this one, then this one, then these 4, which means the most significant byte here, the highest value, actually comes before the lowest value. So when I read it in the network, I'm reading it left. I'm reading them as you see them here and storing them in this array. Not every computer stores data that way. Intel machines actually go the opposite order. The least significant byte is stored first in memory. So we actually have to know what is the default byte order of the internet, which is what we call big endian, most significant byte first, versus little endian, least significant byte first. Now, anybody know where those terms came from, big endian and little endian? Anybody ever read Gulliver's Travels? Yeah, Gulliver's Travels, where there's this war right between these two groups. And they were fighting over which end of the egg you cracked when it was a soft-boiled egg, the big end or the little end. In Gulliver's Travels, do you remember the nickname they gave to the humans on the island where the horses were superior? They were called Yahoos. Have you heard of the company Yahoo? Okay, the computer scientists do stupid things like this. Okay, that's total length. Here now is the identification number of the packet. Here is the flags. Here's a fragment offset. This one wasn't fragmented. One of the flags would say whether it's fragmented or not. That's zeros. Here's the time to live. This one I gave it 40 hex. So 4 times 16, quite a few. 64 pops. Which protocol? This protocol 6 it's going to. Protocol 6 is TCP, Transmission Control Protocol. Here is the checksum. Here is the source IP address. Oh, I hate reading them this way. But 7F is 127. 4C is 76. D2 is 210. And B9 is 185. Here's the destination IP. 7F, that's another 127. Notice there's a bunch of zeros, so 001. So these, you can see these things, you can play with them, you can manipulate them. I just want you to know they're all there. So how does this work? I'm sending these packets across the network and going from one machine to another. I keep talking about these IP addresses, 129.101. something. I want to talk a little more about those. I talked earlier yesterday about last time about class A, B, C, and D networks. Within a single organization, University of Idaho, we're a class B network, 129.101. So anything after that 101 is up to the University of Idaho to organize. And I mentioned before, we can actually subnet that. We can break it down into logically separate groups of hosts within our network. For example, with 129.101, a host would be 129.101.100.1 as an example. We could use this third byte as a subnetwork identifier. This is subnet 100. And then we could have 256 different numbers here, 0 to 255, to deal with hosts. How does that actually work? I'm going to step aside here to this other set of slides. I'll have to change my share. These are borrowed from different people. Credit goes to who they did it. So before subnetting, in any network, any subnet, one can use most of the IP addresses for host addresses, machine addresses. However, I just mentioned, hey, if we're subnet 100, we have 256 possible addresses, 0 to 255. Slightly lied. Address 0 is reserved for that of the network. You can't have a host 0 because you just use that to define what your network is. There's also a broadcast address. That's address 255. Again, slightly lied. It's the highest numbered host address in that subnet. And that goes to every single machine in the network. Basically, it goes out to that address, and every machine on the network looking says, oh, this one just came by. Is it me? Oh, wait, it's a 255. Yeah, it's a broadcast. I should read this. Okay. So let's assume we have a network. This one, instead of doing the 129.101, we'll do 172.19 with a /16 network mask. What does that mean? You will see things written in notation with like /16, /24, /21, whatever. What it says is those last number of bits. So in this case, the last 16 bits are for hosts. So in this case, we have 16 bits, 65,536 possible numbers, 0 through 65,535. With the last one being a broadcast address, the first one being the network address. And our network, our class B network in this case, is 172.19. That's the normal way we write these. All right. I could subnet this into multiple, take this third byte and break it up into subnetworks. To do that, what we do is what we call it as a subnet mask. So this is a /24 subnet mask. We take the first 24 bits and say they're going to find a network for me, right? And what we do is so this would be a /16, this would be /24. Now notice I'm mentioning these masks, and notice these 255s. They're a bunch of ones. When you do mathematical exclusive OR, a 1 exclusive OR to something else is that original value. A 0 exclusive OR, excuse me, I'm lying. We're going to do exclusive ORs. Let's do logical ANDs. A 1 ANDed with the original number is that number. A 0 ANDed with that original number is a 0. So we'll use the subnet mask to basically say, I'm going to take your whole number. Wherever a bunch of these ones are in the subnet mask, I'm going to map that over. That gives me the actual network address. And I'm going to zero out the host number. So that's all we want to do with subnet mask. For years, we were always writing it 255, 255, 255.0 or whatever. And people started saying, well, we just do a /24. We know what that means. So if we have a network, that's my class B network, and I want to subnet my personal network into subnets, I can do the /24, so I can get 255 possible subnets. I can't use the last subnet because it contains the broadcast address, which goes to everybody in my network. So I get subnets 0 through 254, and then each of them has a host number that's possible. So if I do the mask, forget the host part, that gets zeroed out, and these are my actual subnet addresses. So it would be 172.19.1 would be a subnet address. .0, technically they say. They go all the way out. So like this is 172.19.00. Okay. Whoops. So host addresses, the host can go anywhere from 1 to 254. Host 0, that's part of that's the network address. We don't use that. Host 255, that's a broadcast address. We don't use that. Because you have the ability to use the rest. So there's my broadcast addresses. Now, when I'm designing my network, I can have a bunch of hosts on network A, subnetwork A, that's network 0, subnet 0. Network B could be subnet 10, for example. Subnet C could have subnet 5. Subnet D could have subnet 25. And I'll have my router, my switch here, that when messages come in, based on these subnets, it'll send things to the right collection of computers. So right now, the way this is set up, all of these computers would see messages going across this network, but they wouldn't see any of the ones going down here. And so it reduces the amount of traffic. Now, we originally did this when everything was coaxial cable and literally they saw every message. Now we usually have smart switches in our wiring closets that then send it on the precise wire to that precise machine. So in my office, I have 4 network ports coming in from the wiring closet that go to different machines. And so each of those would be separate, but not always. And again, the main router will send it to that switch for my set of machines for network A and won't send anything to that switch for network B. So again, subdivide the work. The switch only had 24 ports. It can't handle more than, so let's subnet it and handle it that way. Now you can only subnet the host portion of your private network. So if we're a class B network, we got 65,000 addresses, we can deal with host addresses. But that 172.16 we had, I can't take, or whatever it was, 172.19, I can't take that 172.19 and subnet that piece because that's other people's addresses. So it doesn't give you more hosts. What it allows you to do is divide a larger network into smaller networks. And you actually lose host addresses when you do this, because each subnet, you lose the address of the subnet, that .0. Each subnet, you lose the broadcast address of that subnet. You may lose the first and last subnets too, because typically people never use a .0 subnet. But again, you want to divide your larger network into smaller networks, so why not? You want to limit the broadcast to the subnets. You can do that. Say, hey, these only go to the machines in this room, this building. Better management of traffic. You are going to see throughout the cybersecurity stuff and network security stuff a lot of subnetting stuff. And so that's why I'm bringing this up. I'm going to be posting a link to a game that does this, that introduces some of the concepts and has you, when you're on the machine, change what subnet you belong to. Okay. Okay, sitting here. Subnetting example, that was the word. Yes.
So we're talking about, because we're talking about each device, right, has their own unique IP on
like this one, 138.101.114.250, right?
Correct. And so let's just kind of filter this down to a practical example, right? So as more and more homeowners have IoT devices and, you know, refrigerators and microwaves and everything, coffee makers, right? You could get to a point, and it might seem excessive today, but let's say you have over 256 devices in your home that have individual IP addresses. Does this translate to IPv6? So then it doesn't matter? Or is this simply, you know, kind of quarantined in IPv4?
So for now, let's limit this to just IPv4.
Okay.
As for the example at home, which I'll get to later, We have a technology called NAT, Network Address Translation. I have a NATed router, almost everybody does at their home. What it does is it allows you to have internal subnetworks, internal networks, and it's usually the 192.168 network, for example. I can have 192.168 is private local network. You can have one, I can have one, he can have one. It's never shared to the internet. And so we each can have 65,000 hosts inside our private internal network. And then the NATed router converts that to the one externally visible IP address, which saved the internet because we're out of IP addresses for years, you know. And the university was mad at me because I want, well, let's see, what do I have physically right now? 1, 2, 3, 4, 5, 6, 7, 8 computers inside my office that would need the unique IP addresses. Okay, I'm lying a little because 2 of them are servers, each running 4 VMs, each with unique IP addresses too. So we're about 16. It all gets added to 1 for the university. So I'm not stealing university addresses. All right. Now, the other thing I want to mention is notice this one. So network mask was /16, right? So it's a 138.101 network. I own everything else. I subnet it this way to a 26-bit subnet. It doesn't have to be the 24. It doesn't have to be, I'm going to use just these first 3 bytes. I'm going to steal 2 bits from this one. And so I'm not going to allow on this subnet 255 machines. I'm going to allow 64. And I'm going to take that 255, break it up 4 times because I took 2 bits from it. So that allows me, you know, subnet 0, 1, 2, and 3. So given the follow, and when you see this, there was something I was looking at, it said, it was a different competition. They said, okay, here's your host IP address. What is the network address for this? The subnetwork address when it's a /26. I was like, oh, and we'll talk about how to compute that, but that'd be 138.101.192. Okay. Given the following host IP address, network mask, and subnet masters, we need to find the major network information. I just mentioned that. That's given these 255, we get 138.101. We need to find the major network broadcast address and the range of hosts, if not subnetted. Then the subnet information, address, range of hosts, broadcasts, and other stuff. How many possible subnets are, number of hosts per subnet. So I'm going to show you how we do this in detail. Here's my information, my host IP, network mask, subnet mask, major network address. I just say, okay, we're mapping just these first 16 bits. So it's just, I can copy just these 2. That's easy. The broadcast address is the rest of the bits. The host bits are all 1. Range of hosts, if not subnetted, we skip 0 and we skip the last one. So anywhere from 138.101.0.1 to 138.101.255.254. But now how do we do this for subnets? Okay. Let's look at the IP address 138.101.114.250. That was my host. Let's convert this all to 1s and 0s, binary. So 138 looks like this, 101 looks like this, etc. We got our mask of 1s. Notice the 2 here for the 192. Okay, because that's these 1s, if you remember, they're you could multiply this number 0, 1 times this number in binary. So this would be as the 1s, the 2s, the 4s, the 8s, the 16s, the 32s, the 64s, the 128s. Just like in decimal notation, this would be the 1s, the 10s, the 100s, the 1000s. So this 128 times 1 plus 64 times 1, that's 192. That's where we get this. If I look at this one, I have 128 plus, let's see, that one's 8 plus 2. So 128 plus 10, 138. Okay, so we translate everything into binary notation. Then we determine the network. So let's find the network mask. Okay, and again, so here's our network thing. This one, what I did, I forgot to mention, is I took all of these numbers and did a logical AND. So wherever there was a 1 here, I copied the number down. Wherever it was zeros, I just made it zeros. This number then becomes my network address, my subnet address. So I drew a line under the mask. I performed a bitwise AND operation. And then I can re-express the numbers as dotted decimal notation. So that's how they do it. Does that make sense? Yes? No? Half of you? So the biggest difference with this mask is where it's all ones, you just copy the number. Where it's partial ones, you just copy those top bits from that host and say that was my subnet mask. It could have been this host was not 250, but try to do the math real quick, like 114 or whatever this is, 112. So it didn't have this top bit, in which case then this would be a 0 and I'd have a different subnet. I'd have 64 for the subnet. So knowing my host address and knowing it's a /26 tells me now what was the subnet, the base subnet of this one. So again, we take this part where the ones are, copy it down. Find the last rightmost 1 bit in the mask. That's where we divide things. Copy the 1, wherever there's 1s, copy it directly. Everywhere else it's zeros, make them zeros. So what we're going to do here is we're going to use terms they use called the great divide and the small divide. The great divide is where you separate for your full network mask, your network itself. And I have no control here. That's why it's a great divide. The small divide is where I have control. I can do my subnet anywhere I want on here. I can move this line anywhere I want. When I look at this, then I can see how many bits are here. So in this case, I have 6 bits. I have 22 to the 6 or 64 possible host addresses in the subnet. Over here, I have 10 bits. So I have 1,024 possible subnets. There's 2 to the 10th, this is 1,024. Notice how I reel off these numbers all the time. You should be able to know all the powers of 2 up to a certain number, you know. So 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 102, 4, 204, 8, 496, 8192, and then I start to stumble.
Yeah.
I have to actually do the math. I remember 65,535 as 2 to the 16th, but that 16,000, that 32,000 one I always mess up on. But you should know those first several. Okay. Just makes life a little easier. Okay, so now what are the first and last hosts, right? So I've got my subnet, I got my list of hosts. The hosting range here, 0 to all ones. The first host will not be number 0, will be number 1 in this range. We then look at this and we combine it with this because we actually have to use our whole 8 bits for the dotted decimal notation. So although it's host number 1, because of this 192, it's 192 plus 1 is 193 is that lowest host number. So the first host is all zeros, a 1 in the rightmost bit, and then when we convert it to dotted decimal, we just take the whole byte. That's what messes almost everybody up in working on this. So my subnet is from 193 to 254, because this is all ones with a 0. Plus the 192. That in this subnet, in the 1, 1 subnet, that's range of hosts. If it was the 1, 0 subnet, I'd be at 192, the highest value, so 191 if I want to avoid the broadcast, down to 129. 128 would be all zeros, so it'd be 129. And so you can calculate, you know, what are the ranges of hosts in each of these subnets. And then when you're assigning host address, you know, oh, you're on that subnet, this is a /26 network, and you're physically plugged into this piece of it, you're gonna get a number from 193 to 254. If I gave you a number of 55, you can't work on that subnet. So here, total number of subnets, 1,024. total subnets, subtract one if all 0 subnets are not allowed, subtract another one if all 1 subnets are not allowed. Some networking topology just don't, technology don't let you do that. So maybe it's 1,022 subnets. Total number of hosts per subnet. Again, now we're just looking at these last bits. 6 bits to the 6 to 64 again, and then we subtract 2, get rid of the broadcast, get rid of the network address, and now we're down to 62 hosts per subnet, which is not a bad number. Couple labs. Does that make some sense? Okay, so this is how we organize things, and this becomes really important when we're looking at where messages come from, where they go to. Is it just within an internal building, internal network? Message comes in and it says, okay, this is 129.101, but what subnet? That subnet lives over in the engineering complex. So it sends it to the engineering complex. In Buchanan Engineering is the main, I believe, the main switch for the engineering complex. And then there it decides, okay, which subnet in our collection has that, which building is that for, and then sends the wiring closet of that building. And then the wiring closet of that building then decides, okay, now where do I break it up? I actually think we are, I don't know if we're using a /26. We might even be using a /21, which means we're allowing more than 255 per subnet. Because those extra 3 bits, we shifted the other way. And I have seen /21 networks, so you add these extra 3 bits. 3 bits is 8. So 8 times, or better yet, we just bring you to 8, we bring you to 11. So 2048 possible machines per subnet. I've seen some of those, I don't like them. All right. Yes.
I know you mentioned like the university uses like smart switches now, so I'm sure there's probably an interface to do all this in, but like back in the day, did they have to like draw it out on paper and just connect the wires accordingly, or?
Oh yes, and even now we still have to draw it on paper and do it. So in each smart switch, so I have a smart switch and say it has 24 ports. They say, well, the port 1 is plugged into this port in my office. Right, because all the wires from all the ports in the office is going to that room. Then they say, okay, that's going to go to port 1 here. They then authorize my office, any machine in my office, to go through that port. And so if you took a laptop with a network card, unplug my computer in my office and plug this in, it could say, no, that MAC address is not authorized for this office. That's what we do with the smart switches. It's all electronically managed now in web and web pages and other stuff where it used to be physically written down, and physically written down with the not having smart switches, so somebody could just swap those cables. Suddenly I could see everything in somebody else's office. Or the dumb switch is what we call hubs. Everything going into that switch went to every other computer, every plug in there. So there's 24 ports, things come in and all 24 machines see it. We try to avoid doing that nowadays. But the important thing is too, with the switches, it may be a gigabit switch, but I have 24 ports coming in, 1 going out. And guess what? The 24 going in are all 1 gigabit ports, and the 1 going out is also a gigabit. Well, those 24 are sharing that 1 gig. Now, usually what they'll do, it'll be a gig going out, it'll be 100 megabits coming in. But again, there are chances you overload the switch. Everybody's doing a lot of things. Typically, they say most machines aren't pushing the envelope on how much data they need, so we can share. So I have a couple gigabit ports in my office. To the gigabit switch, we have a 10 gig link from that switch to the main one in the college, and then 2 10 gigs from the college to the library, which is the library, basement library is where the main router stuff is for the university. That's also where all our files are in OneDrive and stuff. They're in the basement of the library. So I want a fast connection from my office to those and back. All right. Let's see, where am I? All right, let's transport layer. Okay, so I can get it from machine to machine, but I want to do more than that. I want to provide the ability for a user to select and specify acceptable error and loss levels, a desired average and maximum delay, some other, quality of service things. Now, of course, the transport, so I build another layer, but the transport layer is still limited by the underlying internet layer. If the internet layer just can't go any faster than megabit per second, I don't care how fast you tell me the transport layer is, you're not getting faster than megabit per second. One method of doing this, though, in different services provide different transports for different classes of traffic. The main two we deal with, so I have 4 here, is a reliable connection-oriented protocol. There could be a less reliable connection-oriented protocol. There could be a speech protocol requiring sequence timely delivery, or real-time protocols requiring high reliability and timeliness. I should have made this connection list for number 2. But so the whole purpose of the transport layer, of course, is to provide transport of data between 2 transport entities. The user and control data can be on the same or separate channels. So you can think about it as I'm communicating across here, I'm creating this a virtual communication channel. And I can say everything's going across one channel. I can have 2 channels. Here's the control stuff, and here's the data. When we do that, the control is considered out of band. It's using it like a different frequency, like a CB band or radio wave band for communicating things on there. It's a different one. So the file transport protocol that we use uses 2 different channels, one for data, one for control. Full duplex must be supported, although half duplex and simplex may also be offered for special situations. What in the world do I mean here? Almost nobody knows this anymore. Okay, simplex, I'm talking to you and that's it. Half duplex, I talk, then you talk. We don't talk at the same time. Full duplex, we talk at the same time. So especially with the earlier networking technologies, you had to do half duplex because you were sharing the exact same wire for send and receive. And while I'm talking, you couldn't send back because that would corrupt the data. Full duplex supports that. At a higher level of abstraction, we're going to just say, we do that. We're not going to say transport, I'm going to send you data and you can't respond. Why? I need you to be able to respond while I'm talking to say things like, slow down. Or, yeah, I got that, next. Just think you're talking to somebody who goes, Okay. User interface. This could be an application, could be an environment, could be procedure calls from your function calls from your program. Could be passing data and parameters through a mail, some type of electronic mailbox. A use of direct memory access where you just store it somewhere in memory and say, okay, it's there, now grab it. Most of this you don't understand if you haven't taken those classes, that's okay. A common interface would be for flow control with transport users, allowing them to say slow down, stop, hold on, yes, I can go. Timing and confirmation significance, local or remote confirmation. Local confirmation is, as a user of a transfer layer, I tell the transfer layer, I got it, I'm good. Remote is, I tell the transfer layer to tell the application on the other end that I got it, I'm good. Connection management. This becomes a really important thing, especially in the connection-oriented protocols. I have to be able to establish connection. Yeah, we're talking to each other, right? We're going to talk to me. You say yes, I say good. We're talking, we talk until I finally say, okay, I'm ready to hang up. You say good. Now, yes, I can't slam the phone down on you. Yes, we can lose the connection. But the idea is we're agreeing to communicate, and now we have a sequence of communications going on. That has to be managed. Especially if I'm sending a large amount of information across multiple packets. If we have a connection going, I can number those packets and you can say, got 1, got 2, got 3. Oh, 4 is missing, got 5 and 6. Give me 4 again. And you can put them in order and you can deal with all that. If we don't have a connection, you don't do that. Now, your application could say, my application will do this for me, but we want to provide services. That's all what computer science is about. We make lower level services to make things easier for the higher level users. Shared services, shared code. Why do you have to rewrite the code for managing an in-order delivery if I already got it for you? Well, because you're the superstar programmer, you're going to do that. This is what we see a lot in programming. People say, oh, I know how to do this. I'm going to do it. It's already there. Don't reinvent it. Anyway, we can also have expedited delivery. Hey, this is an urgent message. Get it across there. So it can skip ahead of others. We have status reporting. What's the current throughput? What's the mean delay? What addresses are available? What class of protocol is in use? What are current timer values and other things? What do I mean by timer values? We're going to have things in a timeout where basically I send you something. I want you to acknowledge you received it. If you don't respond, I'm going to send it to you again. But I'm not going to send it to you really fast because I know it takes you some time to respond. So I set a timer. And that timer waits until you send me a response. There's actually a couple timers we use. One for just retransmitting a message, another for seeing if I don't get anything back from you, maybe you hung up on me. And maybe I'll just time out the whole connection. So I'm sending stuff off into the bit bucket. No idea where it goes. So all these things we have to deal with. And of course, security, another fine service. So when people put this together and this idea, they said, how do we handle all this? So they created back in the 70s, 80s, two simple versions of this. One is called the user datagram protocol. It is basically an extension of what the raw internet is, but for the user level at the transport. Okay, no implicit error control, no implicit flow control, no guaranteed in-order delivery. It's, I got a single message, I'm shipping it off to you, a single packet, I'm shipping it to you. Let's hope you get it. So we wanted to make that available to the higher level users. It does assume the internet protocol is the underlying protocol. There are some ways of like UDP and TCP over other protocols that are special standards out there, but this one assumes the internet protocol. It does provide a procedure for the application program to send messages to other programs with minimal protocol mechanisms. So I don't just send it. Internet protocol allows me to send it to another machine. User datagram allows me to send my application to send it to your application on another machine. Okay. It is transaction oriented. Delivery, duplicate protection, not guaranteed. The network can accidentally duplicate a message and resend it. That's okay. I talked about headers. Remember on the layering I talked about last time where everybody adds a header. Well, the UDP adds a header. It's a small one though. Okay, I'm going to start at the bottom. It has a checksum. 16-bit ones complement of the ones complement sum of a pseudo header of IP layer info and UDP header info. So it actually assumes an internet protocol header too, and does a checksum on that. And it's pseudo because certain fields are assumed to always have certain values like zeros or whatever. It's a ones complement of the ones complement sum. If you've taken CS 150, you know what this means. If you haven't, you don't, that's okay. The length is the number of bytes in the user datagram, including the header. Now the user datagram also includes the IP header and the IP data, because that's everything the user datagram is sending. Okay, so that's the UDP protocol unit. We have two things in here, source port and destination port. So as I mentioned with IP, it had a protocol number. You know, protocol 6 was TCP. Who do I send this to? Well, each protocol needs to know which application I'm sending this to, which program in your machine is using the service. We call those ports. So my program goes to the system and says, give me a port. Now I'll come back to that in a second. System says, yeah, you're port 255. So that's my source port and I send it out. Now, who am I sending it to? I know you're waiting and listening on port 443. So I send it to a destination port 443 at your machine. Okay, 16 bits. So there are 65,536 possible port numbers. The first 1,024 of those are considered privileged. If you're not, the operating system or a user with system administrator root privileges can use one of those ports to set up a service and say, I'm listening on this port, I'm waiting for communications on, say, port 443. A regular user can't. That's where all the services exist. Then beyond that are the user level services. They've decided some of those are useful enough, and they've actually reserved numbers up there. Port 8080 is an insecure web server. Port 80 is a secure web server. Now, not in UDP, it's actually TCP. I'll just give you examples. The Internet Engineering Task Force has a document called Assigned Numbers that defines what are these major port numbers. If you do a test in Security Plus, Network Plus, something like that, they're going to ask you about port numbers. You got to memorize them. Why? I look them up. I know a couple. Okay. But this is important. Now, notice here, there's no IP address. I say send it to port 443, but at what machine? Well, that's in the IP header already. I'm assuming IP exists. I know it's in the header, so I'm not going to duplicate it. Let's not put in that much extra information. When my machine receives this information, my machine should receive the headers, or at least my machine, when my application is running, it says, hey, you got a packet off the network. I'll say, give me the data. I have a way at least of asking it, what was the port number this was sent from? Why? So I can know who to respond to. What was the machine it was sent from? I can check, was it really sent to me? So those things are all out there. Okay, so I was just talking about ports. It is common in our dotted decimal notation of IP addresses to use a comma followed by a port number to say that's a UDP address, and a colon to say it's a TCP address. Some people are nicer and actually tell you TCP, this one, UDP, this. Not everybody does. So if you see a comma, think it's UDP, colon, it's TCP. Okay, that was UDP, a very simple one. We use this for, there are protocols out there, messaging protocols, voice, video, although we'll use UDP because I'm just, dumping things really fast. TCP is, I want things reliable. It's a connection-oriented, end-to-end reliable protocol designed to fit into a layered hierarchy of protocols which support multi-network applications. This is all from the standard. Basically, it assumes IP. And it says, I want my application to talk to your application in a reliable way. And I make very, very few assumptions about what the underlying network is capable of doing. There will be redundancy implemented into the TCP protocol, just in case, error control, flow control, just in case the lower level screws up. So it provides several services, a basic data transfer service. Hey, it's a way of getting data from my machine to your machine, my application to yours. It's treated as a continuous stream of bytes, they say octets, in each direction between the users, and it packages some number of them up into a segment, a protocol data unit, and sends that through the internet system. Those segments are usually mapped directly to internet packets. Sometimes users need to be sure that all the data they submitted has been transmitted before they hang up. So it puts in a push function that says, yeah, because sometimes the system's like, oh yeah, you're trying to send all this data. I got it in my out buffer, I'm waiting. For one reason or another, we'll explain some of the reasons waiting. So the push function says, make sure you get everything out before I hang up. And we may actually say, I want to make sure the end user received it before I hang up. There's an acknowledgement functions built in to allow me to know the end user received it. It has to have reliability. It must recover from data that is damaged, lost, duplicated, or delivered out of order by the lower level network. So what they do is they assign a sequence number to every byte transmitted. Again, I said it's a continuous stream of bytes. So we have numbers. We number them. Here's byte 1, 2, 3, 4, 5, 6. And it requires a positive acknowledgement from the receiving transport control protocol. So I send you 1,024 bytes. I need you to come back to me and say, yep, I got 1,024 bytes. And that's called an ACK. Now I'll come back to how we actually do that in TCP in a minute. Okay. As long as they continue to function properly, internet system doesn't become completely partitioned, no transmission errors will affect the correct delivery of the data. Because if I don't get an ACK back, I respond. You could also send me a NAC, a negative acknowledgement saying, hey, this was corrupted, this was bad, resend it right away. TCP also allows flow control, allows you to tell me to slow down. Basically what you do is you say, I've allocated so much memory to store incoming messages from you. That's all I can store until I've handed them off to the application. That's the TCP receiver at the far end. Before it hands off the application says it's good. Because we don't know how much you can hold. So say you say, hey, I can hold 4,000 bytes. That's my window. And you tell me, I got, we've got this. You got 4,000 bytes you can send. I can send up to 4,000 bytes. Then I have to wait until you ACK some of them. Now maybe you ACK the first 1,000. I know you've used up, you've given me space for 1,000 more, so I send the next 1,000. Okay, so the window indicates the allowed number of bytes I can transmit until I get further permission. Multiplexing, we want to have multiple applications, processes on your machine able to use TCP facilities, port numbers. Okay. Connections, we want to have the idea these two are communicating with each other and they'll continue communicating with each other because of that sequencing number and everything. We have to establish that, set it up, and keep it going. So the whole concept of a connection. They must be established between unreliable hosts over an unreliable network. So we use a handshake mechanism. We also use a clock-based sequence numbers to avoid erroneous initialization of connections. It's actually what we call a three-way handshake. I say, hey, I want to connect. You say, and I give you some information. You come back and say, yeah, I want to agree. You give me some information. And then I start sending the data. So we'll come back to all of that. And there, we can have some precedents of security in the communication too in the transport layer. So the TCP protocol itself, that generic description of transport layer could be for any transport layer protocol. But for TCP, this is what the header looks like. Again, we've got a source port, we've got a destination port. These are TCP ports. We can have the same port number for UDP and TCP because they're different protocols. We have a sequence number. Notice that is wide. That's 32 bits. That is the byte number of the first byte I'm sending in my sequence. So my sequence starts out at 0. I send 1,024, I say, hey, this is starting byte 0. Your acknowledgement number comes back and basically says, I've received up to byte 1,022. So you send me 1,023. That's the next sequence number I expect to receive from you. Every single TCP packet has an acknowledgement field. You're always acknowledging this is the next one I expect to receive from you. So if one of your acknowledgements was lost, hopefully the next one comes back before I time out and resend. There's an offset value here, reserved, some flags, window. This tells you, hey, this is how many more bytes you're allowed to send me past this acknowledgement number. Check some of the headers and an urgent pointer to say if what part of this data of this whole thing I'm sending is urgent data that needs to really be pushed through. So an example again, notice this is the same data packet that I got across. I had the internet protocol, I had the TCP protocol. Now I kind of lied to you earlier, so I have to be careful. I said things backwards, I think. Here's my raw data at the end. That is wrapped with a TCP header that is wrapped with the IP header. What I think I said it accidentally the other way earlier. The IP header goes is outside the TCP header. It goes first. because it could send to many different things, TCP or UDP or whatever. So again, the UDP here is here. This is what machine gets it, now which port. And the sequence number. Now, for security purposes, when I set up a connection, I say, hey, I want to talk to you. I actually send you a sequence number. I say, and this will be the sequence number. It actually says, pretend this was the number of the last byte I sent you. You'll acknowledge that number and the next number, and that's the one I can send you. I don't start at 0 because somebody spoofing packets, faking packets could say, oh, they just established a connection. Well, I know what bytes 0 through 100 should be, and then, you know, user ID or whatever starts at byte 101, I'll change it and put in byte 101 as my user ID. Kevin Mitnick did that in an attack a long time ago. And so they said, hey, we can just do this. When you do this, send me the sequence number and an acknowledgement, you know, we'll reset things. There's a flag that says, hey, I want to reset the connection, resequence, could give me a new sequence number. The acknowledgement, hey, that's the next one I expect to see. Options field, flags, window size, checksum, and then the raw data. So here's some common TCP port numbers. 20 and 21 are FTP, the file transport protocol. If I remember correctly, 20 is used for establishing the connection and sending the control stuff, and 21 is used for the data transport. Secure shell, port 22. So if I want to do an SSH into somebody, it's connection oriented because we have a communication going. It's port 22. Telnet 23. Telnet is in secure shell. SMTP. Anybody know what that is? Port 25. Email, simple mail transport protocol. IPsec, so security added to IPv4. Domain name services, so we're trying to look up names somewhere. BootP, trivial file transport protocol. Web, hypertext transport protocol. Kerberos, that's an authentication protocol. Did you have a question?
Yeah, so those like common ports, are they, do any of them transfer over between like TCP and UDP, or are they just all?
These are just TCP ports. Remote desktop, 3389. Okay, wait a minute, that's not a protected one because you usually do remote desktop into a user application, a user desktop, not into a root desktop. So lots of these. DHCP, domain host control protocol, that's for getting your IP address dynamically. So lots of, these are just some of them. Secure socket layer, port 443, which is what we use if we're doing HTTPS, secure network protocols. We do it over a secure socket layer, which we'll talk about later. So we go to port 443, then it sends it internally to the application at port 80. We can do things called tunneling too, where I will send it to SSH port here or SSL port here, and then that port will take my data and say, I'm going to send it internally to the actual application because I want to wrap security around it. So how does TCP work? This is our three-way handshake. Host A has a source port 1558, destination port 23. Say we'll assume sequence number 1200. So pretend this was the last byte I sent was 1200. No ACK, I don't know what you're talking about. And I set a flag called the SYN flag. That means synchronize. The host gets and says, hey, this is a SYN flag. Somebody wants to talk to me. What I'm going to do is I'm going to say yes, maybe. If I say yes, I'm going to send back a SYN-ACK. So I'm going to send saying, yes, I want to synchronize everything with you. I want to acknowledge that I received your last one. I'm expecting now to receive 1201. When I get this, A gets it. A says, oh, I sent 1200, you acknowledge 1201, so we're good. I send it to your port from my port. Now, usually what host B also does is it allocates resources, because what I'm not showing this here is like, what's my window size? So host B says, I'm now talking to A. So maybe I'll set aside 4,000 bytes for our communication. and I'll set up some other buffer information about this communication, like what was the sequence number, what's the ACK number, all these things. Oh, that takes up resources on my machine. What if somebody was able to force host, a whole bunch of host A's to send these SYN messages over to host B? It's called the SYN flood attack. And if I flood host B with all of these requests from illegitimate users, host B responds back with ACKs and these users ignore them. Host B then was allocated 4K per message, and I send them, a couple 100,000 of these, it's out of memory. And now a legitimate user can't come in. So we have to worry about lots of these things that happen. Anyway, so it all happened. Now 3 can respond back, ACKing the sequence number from host B. We're all three-way handshake connected. We know what everybody's sequence number is. We know the ports. We know we're talking to each other. I'll talk about some of those attacks later. But some of the things that, actually looking at time, I think I'll stop there. Questions, comments, concerns